All right. Hopefully you guys can hear me okay. How many of you guys have heard a couple presentations about AI this week? Show of hands. All right. So today I'm going to surprise you by talking about AI networking today. So we're going to talk about the NVIDIA Spectrum-X Network Platform Architecture. But what does that mean? We're really talking about extending AI into mainstream cloud infrastructure. My name is David Iles, and I'm a senior director at NVIDIA, and I'm responsible for AI networking solutions and ecosystems. I will not be joined by Gilad Shainer this week, as he is in Israel, dealing with some other very important matters. But let's talk about AI data centers. And when I talk about AI here, I'm talking about big AI, right? This is large language models, things like ChatGPT. And when we see data centers built for solving these problems, we call these AI factories. So an AI factory is purpose-built to do one thing and one thing well, and that is to do the peak level of AI training performance. And by that we mean AI performance per watt or per dollar, but it's the peak. And it's designed specifically for that. And so if you look at the GPUs that are chosen, they are tuned for that. The amount of memory per GPU, the amount of GPUs per server, the type of storage is optimal in that environment to feed those GPUs. Because the last thing you want is an idle GPU, right? You want to have peak utilization if you want the best AI training times. And every data center is defined by its network. And so I'm a network guy. Of course, I see the world that way, right? So every network kind of defines that data center on what it's good at and what it's bad at. And if you were to look at the network for an AI factory, it's really going to have two primary networks. You're going to see inside of the server, in between those GPUs, there's NVLink. And this is a super high speed, 900 gigabytes per second, super high bandwidth between those GPUs. But every time a GPU needs to talk to another GPU outside of that server, it's going to use InfiniBand. Because this combination of NVLink and InfiniBand is perfect for producing that highest level of AI performance in an AI factory. But an AI factory has some unusual qualities. One of them is if you were to go to one of these big GPT training environments, those large scale ones, you might be surprised and say, well, how many tenants do they have in that data center? Well, a lot of them have one. And how many jobs are they running? Well, they're running GPT with hundreds of billions of parameters. That's the one thing they're doing. And that's very different than a cloud environment, where they're almost the opposite. They are optimized for massively multi-tenant environments, so massive. And their networks kind of define them. In fact, if you look at, they run on traditional Ethernet. But when we say traditional Ethernet, Ethernet's been evolving for years and stretching so that it can do this multi-tenant environment, massive jobs running at the same time. And so that network kind of defines what it's good at. Now, there's an attraction in cloud to offer services, new services all the time. And people want to offer generative AI on public cloud, on traditional Ethernet. So what do people do? All right, they take those same GPUs out of that, maybe same servers maybe, and take them out of an AI factory, and they plop it on traditional Ethernet. And so now you've got a bunch of GPUs, and they're communicating with each other. And at NVIDIA, we know a lot about AI, and we know exactly what you should get in terms of performance out of those GPUs. And I'll tell you, when you run it on traditional Ethernet, you get much less performance than you would on an optimized fabric. So we think Ethernet makes sense in the cloud for lots of reasons. People have a familiarity with cloud. They have expertise. They know how to troubleshoot it. All their tools and their tooling are Ethernet-based. Their security is Ethernet-based. A lot of times they've got a whole ghost network that runs alongside that uses packet brokering and the like, and that runs on Ethernet. So you're not getting Ethernet out of the cloud, right? It needs to be there for a lot of reasons. So when we start looking at AI cloud, we say, well, you know what? There's some specialized Ethernet that is built for this environment. And just like the other two environments, the AI cloud is going to be defined by the networks that are running there. Now, you're going to see a lot of people have different terms for these things. Some people call it a back-end network, and then a front-end network. For us, it's about east-west versus north-south. So when you see here we're talking about east-west, we're talking about a network that is optimized for GPU to GPU connectivity. Now, both these networks in an AI cloud are going to be Ethernet, but they're going to be very different. That north-south network, it's optimized for connecting servers to clients that may be on the other side of the planet. And so if you look at the protocols running, they're also going to be very different. So your north-south network, it's running lots of TCP flows, tons of relatively small bandwidth flows that actually turns out they're really easy to load balance when it comes to ECMP. And then you look at that east-west network, well, it's going to be a lossless network, number one, and it's going to be running UDP because it's running Rocky. And the flows there are going to be these elephant flows, massive elephant flows. Turns out it's not super easy to load balance. More on that later. But if you look at you see this high jitter tolerance. We're talking about latency there. And that's where on the north-south, that latency might vary a great deal. Because sometimes you're going to have flows that are going between servers that are in the same rack. And sometimes you're going to have flows that are going from a server to a client on another side of another continent. And those latencies are going to be very different. And so there's never been a reason to optimize. You know, sometimes they measure themselves on the average latency. Average latency is important, but the outlier latency becomes more important. Long tail completion times kill AI performance. And so you've got to kill that like 5%, 4%, 3%, those one outliers that are going to cause a problem. Because AI, and this is really that first bullet here, the AI applications are a lot more like high-performance computing, where cloud is very loosely coupled. AI is tightly coupled. Things are working together. These GPUs are working collaboratively. They'll have collective operations. And you know, the way it works with cloud is, with AI, some people think of it as like a relay race. And if you have one slow guy, it's going to slow down your whole, and you're not going to finish the race on time. If only that was true, because then your fast guy might be able to keep up with it. But really, I think it's more like, you know, getting to the airport. And if you guys all flew here probably, but if you've ever traveled with your kids or your grandma, it doesn't matter how fast you can get to that airplane to make it to the ticket on time. What matters is the slowest member of your party. And AI is a bit like that. You don't want anything that slows down one of your GPUs, right? Because then you have idle time. So let's talk about Spectrum-X, which was built specifically for solving this problem of that east-west network. So it's a end-to-end solution. What do we mean by that? It was built to work with NVIDIA GPUs, NVIDIA DPUs, NVIDIA switches, and the libraries that run on top of it. For very good reasons, right? You want these things to work hand in glove. And so you can see there it says this is a network that's optimized for nickel. Show of hands. Who's ever heard of nickel before? So nickel, NCCL, it stands for NVIDIA Collective Communications Library. And the way to think about it is anytime you have more than one GPU, nickel tells those GPUs how to communicate over which path, what's the traffic pattern. So you can imagine that the network really wants to be tuned for nickel if you want the best AI performance. Now, we're going to talk about some of the innovations we have here, like Rocky adaptive routing on the next page and congestion control. But at the bottom, you can see we've got this combination of our BlueField SuperNICs and our Spectrum-4 switch. Now, you'll look at the specs on the Spectrum-4 and go, hey, it's 51 terabits, it's 100 gig SerDes, it's latest process technology. Boy, that'd be a great north-south switch. And I'm not going to lie, it's a fine north-south switch. But it was designed to be the best east-west switch, right? They designed this thing, it takes years to bring this thing to light, make it production. And so this has been the plan for a very long time, to be focused on that east-west. So let's talk about first innovation, which is our Rocky adaptive routing. So Rocky adaptive routing, it is built for lossless environments only. We're not trying to solve the general case. We are focused, we're laser focused on AI. And so I mentioned before that traditional Ethernet doesn't fare too well when you put AI workloads on it. And part of it is those elephant flows. So with traditional Ethernet, there's kind of a rule. You use ECMP to load balance from leaf to spine, and there's a rule that says every packet in that flow better take the same path. Why? Because if it doesn't, you'll end up with packets that are out of order on the receiving side. And even though things like TCP, they say they know the order, in general, the idea is if in doubt, throw it out and just ask for a retransmit. So with Spectrum-X, we kind of changed those rules a little bit. Because we have both ends of the wire, it gives us some flexibility. So in this case, if you were to kind of go through the steps there, kind of step one, data is getting sent down to the BlueField-3 Super NIC. The BlueField-3 is going to chop them off and put them into packets. And then when it gets to that leaf switch in step 3, that leaf switch now is going to do something brand new, different than a traditional Ethernet. That switch is going to look at the flows and say, this flow, I am allowed to load balance this in a new way. I'm going to use my fine-grained adaptive routing technology to load balance on a packet-by-packet basis and avoid any congested links. So in this way, we're able to achieve 95% utilization instead of traditional Ethernet, which usually gets between 60 and 65% when you put AI workloads on it. So a dramatic increase. But in order to pull this off, there's another piece that needs to happen, which is on the right-hand side, is those BlueField. You'll see the packets are going to arrive to the BlueFields on the right, and those BlueFields are going to need to reorder the packets. So there's a technology that we've talked about publicly called direct data placement. And basically those BlueFields, as they put the packets into memory, they put that memory into the CPU, or past the CPU directly into the system memory, because this is RDMA traffic we're talking about. Or in this case, it actually might go into GPU memory, because this could be GPU direct. Those are reordered as it goes in. And so this allows us to achieve those great results at the bottom where we're getting 1.6x higher throughput. And throughput's important, right? You've got to feed the GPUs. But this is one kind of congestion that we're avoiding. There's another kind of congestion that you have to control. There's no avoiding this. This is called many-to-one or incast. And this is very common in AI, where you've got some collective operations where many are sending data to one. Very common. And in this scenario, you've got, on the upper right, you'll see the normal scenario is I've got two servers using the same workload. They're working collaboratively together, and they're sending two different, we're going to say 400 gig streams. And because these are NVIDIA GPUs, they have no problem filling up a 400 gig pipe. So 800 gigs of traffic are going into the network. They're getting spread, they're load balanced, but there's only a single 400 gig link coming out of the network. So 800 gig going in, 400 gig going out, that's going to be a problem. So what normally happens in the upper one there, whether you're talking Rocky V1 or Rocky V2, those packets start to buffer up. They get past a certain threshold point. They start marking those packets that go out, and then the adapter on the right will go ahead and send a congestion notification packet, and they'll go all the way across the network back to the senders, and everybody starts slowing down. It's supposed to work great. It's this great dance. What we see in today's modern AI infrastructure, modern AI workloads running on traditional Ethernet, it doesn't work so well. We see not only workload A in this case gets less than half the bandwidth they should. There's this other thing that happens to workload B. This is what we call a performance isolation problem. And we see it all the time when you've got multiple AI jobs running on Ethernet. It's not just that the overall number's bad, but you start running multiple jobs and each one gets impacted by this performance isolation. Now in cloud, you guys have probably heard of the noisy neighbor problem. And this is a great example of it. We've got workload B here. It's been chugging along fine, maybe for months. And then all of a sudden you get a noisy neighbor, workload A shows up, and now workload B is negatively impacted. So we solved this using a programmable congestion control technique. And in this case, the BlueFields, they're going to send probes in the network. So these are the ingress, the guys that are responsible for sending the packets into the network. So instead of just flying blind, they're going to have some visibility into the network using these probes, and they work in tight coordination with the Spectrum-4 in a way that the BlueFields can detect when there's congestion and can react at hardware time scales, meaning in microsecond time scales, it can react to congestion and use a fine-grained traffic metering technology so that it adjusts the injection rate. Because to be honest, it doesn't matter how fast you can push packets into the data center if they can't come out at the same rate. And so they adjust to that speed of kind of that egress path. So in this scenario, workload A, each of those guys are going to get nearly 200 gigs each, right, on the left side, and then it's going to reach about 400 gigs leaving. And so they're going to more than double the performance of workload A. But the good news is now workload B, who in the past was getting hammered, they are now getting also their full line rate. Now I mentioned this thing is programmable. Okay. What this means is we've been working with this for quite a while and tuning it to work with the adaptive routing I was just talking about. So it's tuned, optimized for that. It's optimized to work with nickel, which I was explaining earlier. And it's optimized for both 2-tier networks and 3-tier networks. So leaf spine and leaf spine super spine, which for a 51 terabit switch, we're talking hundreds of thousands of GPUs that we can connect, and it's all tuned for you. However, let's say you're like, I'm smarter than those NVIDIA guys, or I've got a network that's a bit different. So what we do there is go ahead and allow you to tune it yourself if you want. Now, I'm just going to have an example of the throughput of each of the flows. And you can see on traditional Ethernet, some of the flows, that elephant on the top, that elephant flow, he's a lucky elephant because he ended up on the one path. He's the one elephant on the link that he's on. And you see some of those guys at the bottom, he's an unlucky elephant, right? He got 4 of them all run on the same 200 gig link. And so whenever you see something like that, you should be thinking, uh-oh, I have a GPU that's idle. I have a GPU that's waiting to get fed what I need. The other thing that happens whenever we have this congestion is instead of those average latency of port to port, which are always measured on switches when there's no buffers being filled, now we've got buffers being filled. And your latency didn't double, right? It didn't quadruple. It exponentially increased, especially in some of the larger buffer switches. And this is one of the examples of where you end up with those long tail problems, which absolutely kills AI performance. Okay, so we're going to build a supercomputer, an generative AI cloud supercomputer. And this is something we've been very public about. It'll use 2,000 of our H100 GPUs. It'll use 2,500 of our DPUs. And it will be the fastest supercomputer in Israel, but it'll be on the top 500. And with these 2,000 GPUs, we are claiming we're going to hit 8 exaflops of AI performance. So we're throwing the bar down, saying, hey, if you want to do it right with our GPUs and our networking, that's what you're going to get. And if you build a 2,000 GPU network or cluster with someone else's network, you probably aren't going to get that 8 exaflops of performance. Now, some of you guys are thinking, hey, this is great, and and just so you know, we allow people to use this today with our Cumulus Linux. It's optimized. However, this is OCP, so there's a lot of people very interested in Sonic. How do we deploy this with Sonic? And we absolutely have a plan for that. We famously we support Sonic, the pure Sonic, meaning we don't have a private distribution, and we're not going to change that. We're going to continue we think the right and proper path for open source projects like this, but we want to make sure that you have the ability to use this advanced technology. So we're going to have a container that we release on what's called NGC, which is NVIDIA's GPU cloud, and that's how we deal with a lot of open source projects. We publish them in containers, and we give you all the kind of stuff that you'd like. And if you're an NVIDIA partner or a developer on NVIDIA AI platforms, you already know all about NGC. But this is the standard way of doing it. And you'll be able to, with this container, enable the adaptive routing. You'll get the programmable congestion control. And actually, there's a bunch of other stuff we haven't really talked about yet, but we'll talk about it later. But the user experience will be seamless for Spectrum, or for Sonic users, because you'll use the Sonic user experience. Now, call to action. We would love for you guys that want to do generative AI clouds to do a POC with us. But we'd also like, if before you could get the equipment, right, you went to our simulation environment. We have this thing called NVIDIA Air, and you can play with Cumulus Linux, you can play with Sonic, and we have pre-built like DGX like superpods that are already set up for you, so you can kind of see what they look like in a simulated environment. And then if you want to know more, we've got videos, we've got all of that stuff posted. Come on up. This is the end of my slide. Unfortunately, I don't probably have time. I have 2 minutes, it says, for one question. One question. You can come over and set up.
Any questions from the audience?
So I blinded them with science.
All right. Right there.
Is this one live? Yeah. It's my understanding that the BlueField architecture is all Ethernet connectivity across the full system.
Oh, good question. So if those that didn't hear, the BlueField it's optimized for Ethernet. And actually, the BlueFields, all of them now, it used to be we would have like one model for this, one model for that, but it actually will do InfiniBand as well as Ethernet. But when it comes to Spectrum-X, we're all talking about Ethernet for AI cloud. So the ones that we're talking about in Israel 1 and the ones that we're talking about doing this technology, it is Ethernet. But we also have BlueField-3s that are InfiniBand, and they are also useful for some of these AI. Great question.
Thank you.